Thanks for the introduction, Harry. So, my name is Tero Karras, and I work as a principal research scientist at NVIDIA. Today, I'm going to talk about our recent paper that just got accepted to the ICLR Machine Learning Conference. We humans possess an amazing skill. When we look at the world around us, we can immediately understand what we are seeing. So, for example, here's a cat. Some of us can even turn this deep knowledge that our brain has about what different objects are supposed to look like into realistic looking pictures. But what about AI? Well, as we saw in Heikki's presentation just now, the problem of detecting and identifying objects in pictures and videos is pretty much a solved problem. Modern techniques can easily learn to look at specific features like shapes and colors and textures to be able to make the call. But if we flip the problem the other way and ask machine learning to produce realistic looking pictures from scratch, turns out that's a much more challenging problem. Because basically, in order to solve that, you will have to understand everything completely that is in the picture. There have been a lot, so the problem is called generative modeling, and the basic setting is that you're given a bunch of material, like pictures, and you want to construct a model that is able to give you an infinite amount of similar looking material. There have been lots of techniques attempting to attack this problem, but by far the most promising one is a technique called Generative Adversarial Networks, or GANs, where the idea is to pit two distinct models to compete against each other. So we essentially have a two-player game. Let's say the first player here is a bad guy who wants to print some fake money. And obviously the second one is the good guy who wants to prevent that. So initially these players may be kind of dumb, so the bad guy might produce something like this. And it's quite easy to tell that this is fake. But now suppose somehow magically if the bad guy was able to read the mind of the good guy to determine exactly how they came to this conclusion, they can then use that information to up their game and produce something much more convincing. And now the good guy looking at this is puzzled and forced to improve themselves in order to again tell that this is also a fake. And the idea is that if we continue this process long enough, both players will evolve to the point where the fakes are indistinguishable from the real thing. So in practice, these models are obviously deep neural networks. There's nothing particularly special about the networks themselves. They consist of standard convolutional layers, upsampling, so on. The first one, the bad guy here, is called the generator network. And its job is to take a bunch of random numbers called the latent vector and turn them into some kind of a picture. Then we have the discriminator network, whose job is to look at pictures and be able to classify them as either real or fake. Typically, the two networks are modeled as mirror images of each other, and they are trained in an alternating fashion. So when we're training the discriminator, we want to make it be as good as possible at classifying images. So as training data, we use whatever is currently being produced by the generator. We feed that to the discriminator, and we want the discriminator to correctly classify these kinds of images as fake. So we do standard backpropagation and update the weights so that it will do a better job in the future. Similarly, we also showed examples of real images from our training data, and again want correct classification, update weights, and so on. But the interesting part is when we train the generator. This is the mind-reading part. So the goal for the generator is to fool the discriminator the best it can. So again, we generate some images, we feed them through the discriminator, but now, since we are trying to fool the discriminator, we actually wanted to misclassify these fake images as being real. So we flip our objective and do backprop all the way through both networks and update the generator to be as good as possible in fooling the discriminator. Ever since their conception, GANs have raised a lot of interest in the academia, mainly because the quality of results that they produce is much better than in any of the competing approaches. But they're not completely problem-free either. So suppose we try to train a GAN to produce images like these. After initialization, before we have actually done any training, the generator will obviously output some random images. But when we start the training, it quickly learns to produce something resembling the same kind of material. But at this point, the quality of the images is kind of low, and there's much less variation visible in the generated images. They are kind of similar looking, similar color scheme. But now one problem is that if we continue the training beyond this point, the situation doesn't typically improve almost at all. So no matter how long we train, we still have the same quality and lack of variation. And what's even worse is that if we continue the training even longer, at some point we will hit a major problem called mode collapse. Bang. What basically happens here is that one of the networks wins and the other one loses, and it's game over. So these difficulties are well known in literature, but the nasty thing is that they effectively put a hard upper bound on the achievable image quality, because if you try to make the networks bigger or deeper or increase their resolution, the chances of these things happening go up at the same time. So the goal behind our project was simple enough. Let's try to fix them. Basically want higher resolution, bigger networks, better image quality, more stable training, all that. Easier said than done, of course. So we have a bunch of things to tackle. We need some training data. We need to do something about those catastrophic mode collapses. Also, when operating on high-res images, training performance is also a concern. We need to drastically improve the quality and variation of the generated images. And finally, we need some way to actually tell whether we succeeded or not. So in terms of the training data, the problem is that the bar is basically too low. So far, the focus in research has been mainly on getting GANs to work in the first place. So the standard datasets are kind of primitive and not demanding enough for our goals. So we decided to roll our own. We took a bunch of celebrity photographs from the standard Celeb A dataset, and then we applied all the image processing mojo at our disposal to artificially improve the quality and resolution of the images, and also weed out the bad ones, take only the highest quality images. Also align, center, crop the images appropriately. And as a result, we got this new CELAP AHQ dataset consisting of 30,000 really high quality images at 1K by 1K resolution. For additional testing, we also decided to go with the standard LSUN dataset. The resolution is quite low here, but the reason why this is interesting is because these are basically random photographs taken by random people representing 30 different categories, and there is so much variation in the images that it's extremely hard to model correctly. Okay, so armed with this training data, let's look at the catastrophic failures then, the big issue. The thing is that with the traditional approach to training GANs, if we aim for high resolution, it necessarily means that the networks are going to be extremely deep. And since we are initializing all the layers randomly at the beginning, neither of the networks really has any idea of what it's supposed to be doing. And because the networks are big, it would take a lot of training for them to grasp even the basics. But by that time, the training would already have failed, so no luck. Instead, we take a kind of completely different approach. We start with really tiny 4x4 images and really shallow, tiny networks. And we keep training for some time. And then when the networks are more or less converged, we increase the image resolution to 8x8, add some more layers to both networks simultaneously, and keep training. And we keep going like this until we finally reach the full 1K by 1K resolution. This approach has a lot of obvious benefits. So, for example, in the beginning, we only have a few layers, and the training is easy. It's easy to get those layers to converge. And then when we add new layers one by one, we only have a small number of things we need to learn from scratch, and we can rely on the existing layers that already know what they are doing. Also, another added benefit is that the training time goes down significantly. Here's a plot of that. So on the x-axis we have training time on a single Tesla P100 GPU, and on the y-axis we have training progress measured in millions of images shown to the networks. And we can see that traditional training proceeds at a constant low speed. We are paying the cost of full resolution all the time. Whereas progressive growing first uses these tiny networks and the progress is extremely fast, and only toward the very end we start paying the high cost. In practice, to reach a reasonable amount of training, we can do that 6 times faster. So in practice, the training looks like this. As you can see, the images produced by the generator are initially blocky, low resolution, but the resolution increases quickly, and the progress towards better and better quality is pretty constant. It keeps improving. At around 10 days in this setup, we reach the full resolution and keep going a bit after that to increase the quality further. So with progressive growing, we can simultaneously tackle the failures and the performance, because it makes the training stable enough so that these mode collapses don't really happen that often anymore. Then what about quality and variation? For those, we propose 3 further tricks to improve the training. First one is a special kind of layer that we add towards the end of the discriminator to basically allow it to not only look at individual pictures, but collections of pictures. So this gives the discriminator the capability to measure the amount of variation in the images. And because it can measure it, it can penalize the generator if it's not producing the right amount of variation, which in turn forces the generator to better match the training data. Second one is what we call equalized learning rate. This is basically a small tweak to the underlying gradient descent formulas for updating weights. The point here is to ensure that both networks and all the layers are at an equal footing in terms of how fast they learn. So essentially all the layers are being updated at exactly the same speed. Third one is a new kind of normalization scheme that we apply in the generator. The point is that we are not really limiting the capabilities of the generator in any way, but instead we are discouraging certain kinds of broken images that can typically lead to this kind of an unhealthy competition between the two networks, ultimately leading to the mode collapses. So when we combine all four tricks, the training becomes stable enough to allow us to go all the way to the 1K by 1K resolution with pretty high image quality. Here's what we can get out of the generator. The important thing to note here is that none of these people are real in any meaning of the word real. The generator is essentially combining, mixing and matching different features of human faces in novel ways based on the random inputs. And if, for example, we try to scan the training set for any kind of a picture that looks the same as this generated one, we don't find any. What's pretty fun is that the generator itself is a continuous function. So we can basically see each generated image as a point in the high dimensional latent space, the input space of the generator. And if we have two such points, we can imagine interpolating between them, just traveling from one to the other. And because it's continuous and every point in between is supposed to produce a realistic looking image, we can basically morph any face to another. What's even more fun is just to let the generator wander around the latent space freely to dream up whatever it wants. And that looks like this. It's pretty fun to look at these videos, but the important thing to observe here is that what the generator is doing is semantically meaningful. When we're morphing from one face to another, the changes are kind of natural. The expression is changing, skin color, hair color are changing smoothly, hair is growing, changing shape, the 3D rotation is changing in quite natural way. Not all of the pictures are perfect, but the overall quality is kind of surprisingly high. Here it is also interesting to observe the variation. We have lots of different ethnicities, different types of people represented. All the images are produced by the same network, and we can morph between any of them. Here's a similar set of example videos for the LSAN categories. And here I should stress that most of these categories are extremely hard. This is the first time anyone has even dared to show generative results for most of these categories. And well, nevertheless, we can see that the generator is kind of doing a sensible thing. Looking at the cars or say conference rooms, you have a relatively realistic looking 3D rotations, color changes, room is changing shape, TVs are growing and turning into like photos on the wall and so on. And basically whatever happens to be in the training data, the generator will have to replicate one way or another. So for example, we can see some text labels in some of these cases in this weird gibberish alphabet, but it kind of looks like text. So while there is still obviously some way to go to reach like full photorealism in these cases, this is much better than anyone's been able to do so far. So at this point, I think it's okay to check the quality and variation box as well. The final question is evaluating the results. Are they any good? Well, at first this might seem trivial. Just look at the images and, you know, do they look any good or not? But in fact it's much harder. For example, here's a small sampling of faces produced by one network, and here's another. Which one of these is actually better? There's so many different things going on in here, like what is the quality of the individual images? What's the variation in the color scheme? Are all the ethnicities represented? And so on. And by looking at the pictures, it's impossible to tell, like, is one of these better than the other? And the question is not even about which one is better, but which one is closer to the training set. And then again, the training set is huge. You can't really browse through it and get a good understanding of what the images should be like on the average. So for that, we propose a new metric that we call sliced Wasserstein distance. What we do is first generate a large number of images and extract tens of millions of these tiny 7 by 7 pixel neighborhoods from them. And then we view these neighborhoods as points in high dimensional space. And comparing this point cloud against that of the training data, we can then use existing techniques to actually measure how close these point distributions are to each other. And as a final thing, we can repeat this same process on every different scale of the images to measure different aspects of the images. Here's an example of what kind of observations we can make. So this plot shows the traditional GAN training approach. Again, x-axis is training time, and y-axis is the output of our metric, lower is better. And the different curves represent different resolutions. So here we can see that at first the quality increases quite quickly, but then the progress kind of stagnates, as I showed in my earlier example. But then with progressive training, the situation is kind of different, because the lowest resolution converges really quickly, and then when we increase the resolution, these other curves kind of quickly drop one by one, and in the end we get to a much better place than with traditional training. And this comparison was for a relatively small resolution to, you know, basically get anything out of the traditional approach. Okay, so the interesting question is what's the importance of this? What can you do with something like this? And it's important to point out that this project was basically about basic research in machine learning. I would say that we reached a pretty important milestone in terms of the general capabilities of machine learning. Now we are not only classifying and detecting, but we are actually generating new content. And as such, we didn't really have any particular applications in mind for this project itself. But in the future, it's not difficult to envision a lot of potential interesting use cases that this new capability opens up. Perhaps the most obvious one is image editing. So the thing is that in order to produce these realistic images, the generator must have a lot of useful information about what it is that makes pictures look realistic. So can we somehow tap into that? Here's one simple toy experiment that I did to illustrate. So I'm attempting to combine two different faces together. The way I do it is I take a pre-trained generator and break it into two halves. Then I evaluate the first half separately for two different latent vectors and simply concatenate these activation tensors together to get this kind of conflicting information. And then I feed that through the remaining layers that somehow have to deal with the conflicts. And it works surprisingly well. So in this video, the left-hand side stays still, and the right-hand side is undergoing the same kind of random latent interpolation that I showed earlier. And while the problem is kind of ridiculous, it cannot be solved, the generator is still kind of trying to do its best to match these conflicting halves together. In many frames of this animation, if you stopped it and looked at it for a second or two, you might not be able to tell that there's anything wrong, actually. Another interesting case is digital humans. So we all know about the uncanny valley and how difficult it is to synthesize plausible-looking humans, like video of a human speaking, for example. Maybe we could overcome that. Here's another toy experiment. I took half an hour of YouTube video from some random guy talking, and I used the individual frames from this video as training data for the networks. I didn't train for too long, so resolution and quality are not that great, but first of all, the generated image looks like the same guy. There's no question about it. And when I start doing random walk in the latent space, the guy is kind of doing the same things he's doing in the original video, but it's all generated. So now one really interesting question is, could we gain more control over what the network is doing? What if we could control the opening and closing of the mouth, the orientation of the head, the expression? Maybe we could also generate audio to go with the video. I think the possibilities are kind of intriguing here. Also, one big topic is digital content creation for, say, movies and video games. Today, it requires immense effort and money, and maybe as a result of future research, we use generative techniques to produce whole 3D worlds semi-automatically. What I'm personally really interested to see is what other people will be able to come up with building on top of our stuff, because it's actually all publicly available. Source code, networks, videos, images, training data, everything. And in fact, we are planning a major new code release next week's Friday, because we have spent a lot of effort speeding up, polishing the implementation. It's now running about 21 times faster than before. So if you have enough hardware, you'll be able to train these things overnight. Thank you.